Right, we're going to move on to our next presenter. Oh, no trigger warnings here, unless you're intellectually challenged. I think it might be quite challenging and stimulating. So we're going to hear a fascinating presentation by Dr. Chris Empson. Give it up for Chris.
Ready. Good evening. So I'm going to be talking tonight about quantum mechanics. Before you all groan and start despairing, I'd like to read this quote by my favorite physicist, Richard Feynman. And I think that this quote means that if you go away tonight being really confused about quantum mechanics, then I've either explained all this really well or really badly. I love quantum mechanics, and I'm going to start talking to you now about one of my favorite quantum mechanics experiment, and it's the one that really got me into all this sort of stuff. So Thomas Young first invented what's called the double slit experiment in 1803 to explain his wave theory of light. So this is the experiment. This is kind of a bird's eye view of the apparatus. So on the far left-hand side, we've got a laser. Then we've got a screen, which is totally opaque, with some little slits in it, some little gaps. And then we've got a detector on the far right that's going to show us what's come through the screen. So we're going to start by chucking some ball bearings through the apparatus. You wouldn't do this with a normal physics experiment, but we chuck the ball bearings through the screen, and we see that they hit the detector at the far right-hand side, and you get this kind of little pattern on the far right, all exactly as you would expect. So now we have two slits in the apparatus. So we're chucking more ball bearings through, and they're just forming these two neat little patterns on the far side. All very nice and normal. Now, when you do this with waves, you get a slightly different result. If you put a liquid through here and you start agitating it, you get these peaks and troughs, and they pass through the screen, and then they start propagating out of the slit, and they hit the detector with the most force in the middle, and then the least force as they go out to the side. Now, when you've got two slits, you get this interference pattern because the peaks and the troughs start interfering with each other, and you get these kind of bands, and you get this interference pattern that's on the right-hand side. Right, that's physical stuff. Now we're going to go quantum. And in the quantum world, things behave really weirdly, okay? So if you don't get this bit, you're not dumb or anything, like nobody really understands it, so don't worry. So we're going to start firing photons through the experiment. You could use electrons instead, it doesn't matter, it all works the same. So we're going to start firing them through one slit, and you can see we get this one single band at the back, just as you would expect if you were chucking a physical thing through the apparatus. Easy to understand. But now we're going to put two slits in the apparatus, and hang on, wait a minute, we've got an interference pattern on the far right-hand side. Now, what is going on here? When you've got one slit in your screen, the photons behave as particles. When you've got two slits, they behave as waves. Okay, that can't be right. That's weird, right? What is going on here? So what we're going to do is we're going to start firing single photons, just one photon at a time, out of our laser, through our screen, to hit the detector. Now what's going to happen? We got the interference pattern still. Whoa. So you're firing a single photon through there. The only thing that's there for it to interact with is itself, which means it's passed through both of those slits at the same time, interfered with itself, and hit the detector. What is going on here? Okay, so that's impossible, surely. So you can't have a photon going through both slits at the same time. That's cobblers. So what we're going to do now is we're going to put little detectors over each of the slits, and we're going to detect which of the slits that photon went through. But when you do that, you lose the interference pattern. It spontaneously disappears, and you get two bands on the detector. It's as if it knows it's being watched. Yeah. So, yeah, clever photon. So what does all this mean? I mean, I've told you about this. So what does this really tell us? Well, it tells us a number of things about how the quantum world really works. And the first thing it tells us is that, it confirms Heisenberg's uncertainty principle, which says that you can't know the position and the momentum of a quantum mechanical particle at the same time. It's not possible, and this experiment kind of confirms that, and this is a big deal in quantum mechanics. This is a big one. And the other thing is that it confirms wave-particle duality, which is a bit of a weird concept because it means that a photon, or any quantum mechanical particle, is a wave and a particle all at the same time. But I think that sooner or later another level of theory, like string theory or whatever, will confirm that this is kind of like two sides of the same coin. And finally, it says that the experiment shows that quantum mechanical particles can be in more than one place at once. And when you do the maths, they're actually flying through the slits every which way possible, all at the same time, and really weird. So if you don't understand any more about quantum mechanics, don't worry, nobody really does, and thanks for listening.
Dr. Chris Empson. Fascinating.